interested in the applications.
That's you.
We usually call that engineering. So, generators. All right. This looks probably a lot like something else we saw. What other picture looked like this?
What?
I
forget.
Well, we talked about motors, right?
I thought
What
this
was
was.
the difference with the motor?
I thought this was that.
Electric
Oh, it's touching a wire.
Yeah, so this once again, it's turning, right? It's turning, it's in a magnetic field. But before, we had a battery here.
Yeah.
So the battery would drive this thing to turn. Now it's turning and we're collecting energy, right? So now what we want to do is we want there to be current, and then we have some sort of resistor, and we use that to either create heat or something, and we store the energy in some other way, okay? But here, this thing's turning. Now it's creating energy going the other way. Okay, so we're taking mechanical energy, we're changing it into electrical energy. All right? So this is a loop rotating with some angular frequency omega. What's the flux through the loop?
Well, doesn't it change?
At what point?
Yeah, because it spins.
Right. So what should theta be? So what's omega? What are the units of omega?
Revolutions per second.
That's frequency.
Oh, rotations. No, it's the same thing. Omega is angular speed, so it's speed. So something per second. Rotations per second.
Okay. So frequency is rotations per second.
I don't know what else it would be.
What are we looking for?
Right?
Okay. Omega is 2 pi times frequency. So what are the units?
Oh, radians per second?
Yeah.
That's right.
Okay.
So how do you get radians by itself?
Times by seconds? Sounds like.
Yeah, times it by time.
Yeah.
So you want your angle, right? It's going to be omega t. Okay? So the flux, right? The flux through the loop is A times B. These are both constants. Cosine theta. Cosine omega t. Okay, that's the magnetic flux. So if you want to figure out what kind of current this can give you, right? If we want like the voltage, we can have negative d flux dt. Well, that's AB omega sine omega t. Okay? And that's your EMF. If you want the current, how do you get that? You have voltage. How do you get current?
Divided by R.
Divide this whole thing by R. Now you have the current for your generator. Okay? So all of this just comes from this rotation. If you have something that's rotating, so how would you end up getting something that's rotating? How do you get this mechanical energy to transfer it into electrical energy?
Change the magnetic field.
No, the magnetic field stays constant. Why would you have something turning? What could you use to turn something? Water, right? So hydroelectric dams use turbines, right? You can use windmills. Those can turn something that can then generate current. So you can turn mechanical energy from wind or water or, I think that's it, wind, water, okay, into electrical energy. All right. Hamsters, yes. Oh, yeah, you could. It wouldn't be a lot, but you could technically.
Are you sure? That was going fast.
Oh man, now I want to like make because I don't want to own a hamster, so maybe we just make like a big hamster wheel and we make somebody like run on it.
Competition should make the most power in a minute.
extra credit.
Yeah, I always wondered why like
Where are we gonna
gyms
put it,
didn't
though?
use like
Just have it loose.
like the machines that like powered the gym.
Yeah, well,
But
because then people actually have to use them. And when nobody worked out, they would put
actually, there was somebody. So it depends on your energy needs. I think gyms are just like really energy costly, so that's not a super efficient way to do things. But like if you live like in the middle of nowhere and you don't have very much electrical power, you just have like one LED you need to light and maybe like something to heat water,
Who's living in a house
then
with one
you can
light?
probably use like a
Some crackers.
bicycle to like generate power for your house. But
Fucking feral ass
anyway.
people.
if you're off the grid. So this is sort of a visual of what's happening here. So something turns, and then you can use that to either store. You can either put energy in and it makes something turn, or you can have something turning and you can store the energy. It goes both ways. Okay, so you can take electrical energy and change it into mechanical energy, or you can take mechanical energy and store it as electrical energy. All right, and this is basically the math. All we add if we have more than one loop is you multiply the flux through the loop times the number of loops. Okay, so remember when we did this, how many loops is this? One, right? So if we had 5 loops, where does that come into play? Well, when you're doing flux, right, then the area, if you have 5 loops, is 5 times the area. If you have 1 loop, so you just put an n here, and then this becomes, well, this is still 5, so there's an n over here. Okay, so if you add more loops, you're just adding area. So that's just more area. So just n times a. Okay, so yeah, that's how this works. This is what we just did over here. Okay. We also have transformers, which we kind of did in lab. Not like Optimus Prime, but like the boring kind of transformers that are useful. Okay, so this looks a lot like what we had in the lab. Here's our source. Now this is these are used for AC because as you know, if it's DC, what did you have to do to get it to work?
Disconnect it and then put it back in.
Disconnect it and reconnect it, okay? Which is basically creating like a really low budget AC power source, okay? So you have change, it has to be changing. Why?
To have a current.
Yeah, you have a time derivative, right? So if your flux is constant, you don't get any induced current, which is not very useful, okay? So here we have our primary coil. It's powered by something, okay? Here's our secondary coil. And we have this situation where the flux through this has to be equal to the flux through that. And now why is that? You can't lose flux. Well, what keeps the magnetic field flowing continuously? This core, right? The iron core. Okay. So this doesn't totally work if you don't have something that can make sure the magnetic field lines going through here all go through here. Okay. So the iron core ensures that whatever B is here is also B over here. Okay. But the thing that's the same on both sides is the flux. Okay. So flux 1 is equal to flux 2. Okay? So remember, we have V, right? V is d flux dt. And the fluxes should be equal. Okay? Yes?
Will that depend on how many turns are on the coil?
Yes. Okay? So if the fluxes are the same, you end up with V equals d flux dt. So let's set this up. So we have the first voltage, actually this is called V in this case. V1 is equal to, and we'll pull the N out just to make it a little bit more obvious because it's going to be the magnetic field through one loop, that's the flux is going to be the same, right? So it's just for one loop that the flux is maintained because the magnetic field is the same and as long as the loops have the same area, right, that means the flux is the same, but the number of coils is not. Okay, so we're going to call this N d flux dt. Okay? over N1 is equal to d flux dt, which should be equal to negative v2 over N2. Alright, so you just end up dropping this and you end up with v1 over N1 is equal to v2 over N2. And this is how you can change voltage by just counting the terms. Yes?
Why is V1's N negative?
What?
The negative sign on the N1?
Oh, the Faraday's law says that, remember, the change in voltage opposes the change in flux over time. So there's just a negative sign in this definition, right? It looks like this. So there's always a negative sign.
Oh, okay. So those two don't have to be opposite? That's what I was.
So these both have a negative sign. That's just by definition.
Okay.
We just pulled out the N from the flux because we know this only is true for one loop at a time. Okay, and since they have different numbers of loops, the total flux here and here isn't the same, but the flux through each individual loop should be the same.
Okay.
The same area, same magnetic field. Yes.
Why'd you drop the negatives for those?
I took a derivative of cosine.
Okay.
Negative sign.
Okay, but your definition is sigma, or not sigma, epsilon over r, right? So if you're taking that and putting it, is it not di over dt, or d phi over dt?
Yeah, it is, right? Phi is this. It's positive.
Okay.
Okay, when you take it, so this becomes
Okay. Gotcha,
negative. There's two negatives,
Okay.
and they cancel. Yeah, because one negative comes from the definition,
And
the other negative comes from the derivative of the cosine. Okay. So anyway, if you want to make a transformer, here's your initial voltage, V1. You just have to have the ratio of your turns the way you want it. So if you want to go up in voltage, right, that means this one should have more turns. If you want to go down in voltage, that means this one should have more turns. Okay? All right. So primary voltage, secondary voltage. When are transformers useful? Well,
Stepping up and stepping down power.
yeah, stepping up and stepping down power. Where do you want high voltage?
Power plant.
Not actually so much power plants. High voltage is really useful, right? High voltage, high current is really useful for transferring power because you have a lot less loss if you have a high voltage power line, right? So the amount, nothing is 100% efficient, but you can increase the efficiency by having high voltage in the transmission lines. Where do you not want high voltage?
In your house?
In your house, right? Because you don't want to be electrocuted. And so you want to step down the voltage as you go into like neighborhoods and houses so that you don't electrocute people. Okay? So yeah, generally you actually step up. So you have your power plant, right? It's about 12,000 volts, which is still high voltage. Okay? You step it up to about 240,000 volts. That's what goes through the transmission lines. Okay? And I'm sure you've seen something that looks like this at some point, right? Then you have another step down transformer at the substation. Now you're down to 2,400 volts. Now you have the lines that go out into the neighborhoods. That's going to bring you down to 240 or 120 volts when you get to your house. Okay? And is this AC or DC?
AC.
AC. Okay? Why do we use AC power instead of DC power? Better over distance, because DC, if you want power from the power plant, the electrons from the power plant have to make it all the way to you. Okay, you're moving individual charge over large distances. What does DC do? What?
You just said DC.
You just explained.
I mean, so what does AC do?
It fluctuates the drag speed. And just barely pushes a little bit.
It jiggles the electrons back and forth. Okay, so it's more like a little wave. That's a good
Isn't it like those little ball things that you drop?
So if I'm an electron over here and you want to power something at the other door and you use DC, I have to get all the way from there to there. AC is like if there's a bunch of us and when I wiggle, right, the next person wiggles and the next person wiggles and the wave travels that way. But you don't have to move a physical object from here to here. You move a wave. And waves don't have mass the way that physical objects do. So it takes less work to get the power from here to here. That means you get less loss in the transmission. Okay? So you have electrons all the way along your line, and they all just wiggle back and forth. Now, as far as most like resistors, for instance, almost all of our household items are powered by some sort of resistor. They don't care which direction the current's going as long as there's current. So the current jiggles, and they're like, okay, well, we're going to light up either way. So this was the big fight between Edison and Tesla. And the big issue is if you want to use DC, you have to have power plants every couple miles,
That's gross.
which people would not like.
Yeah.
People forget about power
Then we
plants.
turn into Russia.
Everybody likes having power. Nobody wants to have power plants. So tricky. Unless your power plant is solar panels, then everybody wants those.
Yeah.
But yeah, the way that the stupid thing about this is even though AC is clearly better for a lot of reasons, Edison was a lot more charismatic than Tesla because he was like a pretty good businessman, and Tesla married a pigeon. So I mean, lots of people liked
I wouldn't give
Tesla.
you very much credit either.
Yeah, I mean, lots of people like Tesla that understood him. I mean, he was friends with Mark Twain, so he wasn't like a...
Yeah, but Mark Twain was an asshole too.
Yeah, he was a weirdo, okay? And Edison was less of a weirdo, and they were like, there was this like, I don't know if you guys know, this is like big war between them, like where they're trying to prove the other person was terrible. And like, I think Edison was like electrocuting cows, and he was like, this is what AC does. And I was like, well, also DC.
I don't think it
can
was
do
for
that.
that reason, but he was electrocuting cows. No, elephants.
But actually the
It
way
was
that,
elephants. Yeah, circus elephants.
oh yeah, elephants.
He's like, look, this is what AC can do. Kills like.
That's
elephant.
actually an interesting
Pretty sure it wasn't like that
backstory.
either. I think it was because like elephants, they would trample the circus performers, and it was that way of putting them down.
Well, they were gonna put the elephant down anyway.
Yeah.
It was
How do you
it was
know
a different
this?
time.
Huh? Bob's Burgers, dude.
Actually,
Bob's
there's a
Burgers.
really good,
Yeah.
I think there's a really good drug history about
It's a
this.
fuck. It
I
was
was
fucked
gonna
up.
say, sounds like drunk kids.
Edison was an asshole.
Yeah.
Tesla was a weirdo.
Yeah, that's the so Edison was an asshole. Tesla was a weirdo,
Yeah.
but Tesla had better technology and it went out in the end. But actually, the way it went out is his system was used to power the Chicago World's Fair,
Yes.
which was like this whole big thing that was really pretty and had lots of cool technology. We don't have World's Fairs anymore.
Well, we can't trust anybody
It's too
anymore.
bad.
Fucking kidding me?
Yeah,
If you ever want to read a really good / horrifying book about the Chicago World's Fair, I don't know if you guys like reading, but it's called. There's a book called
What's that?
Devil in the White City, and it is a nonfiction book about a serial killer that was operating during the Chicago World's Fair. He was like I think he technically was a doctor, or he said he was a doctor. He killed like.
Like trap houses. Right?
Oh my god, like, yeah, he had like
Yeah.
trap doors and secret,
Crazy.
it's like he was a terrifying person.
And they
He
raided
owned
his
a
house
hotel
there was,
and,
like, 100
yeah.
bodies in there.
Hotels,
Yeah.
But it also,
Yeah.
so that part's like gross and creepy, but the rest of the book is about like constructing the World's Fair and like the history behind like how they got things done and like the sheer scale of like the architectural and electrical and like the guy who did all the landscaping for the Chicago World's Fair is the guy that designed Central Park in New York. So it's like a really interesting story.
When was that? Like early 1900s?
I think so, or like the late 1800s.
We did a lot of shit for the World's Fair. We built like one of the famous United States landmarks for it. Fucking.
Well, I mean, a bunch of
It's
really
a Small
cool.
World came from the World Fair.
Oh yeah, Balboa Park
Oh, wow.
is
Yeah,
from
Balboa Park.
the Panama
Mm.
Exposition. Yeah, I mean, yeah, that was that was actually like my favorite era of architecture. It's
Yeah.
very whimsical, but anyway, Chicago is like one of the prettiest architectural cities
And one of the most
in the
horrifying.
U.S. Yeah. Well, I mean, not the pretty part.
No, pretty part's great. Southside's terrifying.
But don't go. Yeah.
That deep dish.
That deep dish, fuck deep dish people.
Okay,
Fat
we're
ass.
gonna get to that.
some
Also,
cheesy cake
metal
with tomato
detectors
sauce on it?
run on
Fuck
eddy
outta here.
currents. Can we think of other things that use induction to detect things or read things?
Yeah.
No, that's actually a slightly different mechanism because that's just creating ones and zeros, reading it with a laser. So, but close to a barcode scanner.
Magnetic strips.
Magnetic strips, right? Credit card readers.
That's what I was telling you a good story about that.
Okay. Yeah, which led to me getting in a fight with a bonds checker about how
Oh, you're one of those people?
credit card.
Yeah.
I want to
So,
be
like-
the fucking manager.
No.
Oh.
With the baby in the
This is
car
a
still.
no, this is beforehand. So,
Kids like,
okay,
Mom, can we just go?
how does this work? What's on here?
That's a magnet strip.
Yeah, that's what it's called, right? Why is it called that?
Is this a strip of magnet?
Yes, it's a strip of tiny magnets, and basically you have magnets under here. The orientation of the magnets gives you the code for your credit card, I think in binary, okay? And it repeats 3 or 4 times, right? So as you swipe it, it gets a number, it checks the number, and then it's like, okay, that's the card, and then it sends the information to the bank, and the bank says, don't pay for this. This person is broke and they're lying to you. No, so I swiped my card and it was pretty beat up out of bonds, and it wasn't working. And the checker doesn't want to enter the numbers because
Manually,
that's
because
the
that
other
takes
option.
work.
Yeah. So he's like, oh no, I have a trick for this. So he puts it in like this was
A
back when we
receipt.
had grocery bags.
In the bag.
Okay, so he puts it in the bag and he swipes it through and it works. And I was like, I hadn't seen that before. So I was like, oh, that's really cool. How does that work? And he goes, it's static. And I was like, what? He's like, it's static electricity. And I was like, I'm not sure how this works, but I'm like 100% sure
It's not.
it's
that.
not static electricity. And he's like, trust me, I've been a checker at Vaughn's for 10 years. I was like, no, it's definitely like magnetic induction. Like there's some sort of coil in here that's reading the changing magnetic field. And he's like, I don't think so. I think it's static.
Do this shit every day.
And then my husband said we had to go.
That's like. You know when like
Stop
you
arguing.
grab like
He's
a
just over there
valve
like,
to
not
open a
again.
jar
Yeah.
to help create like
More friction. Yeah.
That's like
Yeah,
that,
in
and then
fact, that
there's
made
like
me-
No, I figured it out.
it's electricity. Like,
Because I was really pissed off when we left. So
You do.
each magnetic
Yeah,
dipole,
Army.
right?
Yeah, it's crazy.
How fast does the signal drop off? Like what's the range? Inverse squared, right? So the force, right, and how it generates, that drops off as inverse squared. Okay? The card reader has a particular width. Like it seems like it's just the size of the card, but it's not. So when you swipe the card through, when it's damaged, there's something called the signal to noise ratio. Okay? And that's if your card's damaged, it's gonna give you some signals, right? It's gonna detect some part of the code that's wrong. And so when it's checking it, you need to have at least 2 of the numbers match. Okay, 2 of the like whole series of numbers match. And so if it's really noisy data, it can't identify which numbers it's reading, and then it gives you an error. So what the bag does is it actually just creates a uniform spacing between the card and the card reader. Because if you, like let's say you have this gap, if the card's in sideways a little bit, right, then these numbers are going to be detected differently than these numbers. So all you do is, it just creates an even spacing, and that gives you a better signal-to-noise ratio. And if your card's not completely screwed up, and it's still got some information there that can be read, it's easier to read it.
Yeah, that makes sense.
So obviously I went back and told the launch.
So
You're
who
fucking stupid.
And he did not care.
Because
So-
it would have worked with the
Yeah.
Who decided to even test this out? Like, who's like, oh, maybe if I put it in a plastic bag and swipe it, that'll work.
Well, think about it. I mean,
Well, these bond check, like if you're a checker, right,
bored out of
you're
your
just
mind.
like trying all kinds of different things.
Yeah, I mean.
Well, not even that. Like, it's simple, man. You're like, oh, it must be in like there must be like wiggle room, so eliminate the space. Well, I'm not gonna like print up a ton of receipt paper for that. Just use a fucking plastic bag.
I don't know.